Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students. So today is the I think third or fourth lecture with third lecture I think um, with electrostatics, maybe fourth lecture with electrostatics. So today what we want to do is we want to go a little bit further with all the material, and also I want to give you a perspective in terms of when you take in the for the NEET JEE students, when you take the exam, what the weightages are. Okay, and we'll quickly go over some of these things, then we'll continue the lecture. Okay, so now I'm going to present. So all right. So today we continue with electrostatic fields, but first I will give you some introduction. Firstly, where do you go to download the application? You go to Play Store and you look for com.nyanamarga.sushruta if you're a NEET student. You know, if you're a JEE student, you should go to com.nyanamarga.ramanujan. Okay, so download the application on an Android compatible device. This is very important. We does not work on iPhone. It only works on Android compatible device. It has to be either a cell phone or a tablet. The tablet is preferable because little bit bigger screen, because to read the NCERT textbook you need to have a bigger screen. Otherwise, you can go for our tablet solution, which is little more expensive. But this is a very good app. You try it. You if you like it, then you buy it. It's very low cost. You will see that it provides a lot of value to you, and you will get value for the money. Okay, so this is the formula sheet. It is from your NCERT book. Okay, this sheet you must know. Okay, so notice all the formulas needed for electrostatics is here, in one sheet. Okay, and all the terminology also is here. So learn this very well, and our aim is to make sure that students learn all the material well, and they pay attention in the class, and then they solve the problems. So today we are going to do some problems. So but before I go there, I want to tell you, you know, uh, give you a rough idea of the weightage. Lot of students, they later find out and then they say, I didn't have time to complete my preparation, right? Don't do that. I have actually covered last year, in the last 8 to 9 months, the full, all the main topics. Okay, we have covered all the topics in this. We most recently covered heat and thermodynamics to complete the year. We did that at the end of the year, and then we started with electrostatics. Now, so you can get all this material from my previous lectures. You know, but now what we are covering is electrostatics, right? Electrostatics magnetism is this portion, is the yellow portion, and then along with current electricity, it is about one third of the exam. Another one third is going to mechanics. See, right now, the class 11 students, we are doing mechanics, right? The class 12 students, we are doing electricity, magnetism, and then electromagnetic induction and current electricity. So these are two parallel tracks that we are taking, okay? So one day you come for this, one day you come for that. But first you must know some mechanics before you can learn, as you will see today, okay? So this is for the NEET students, okay? So the NEET weightage is distributed like this, okay? We already covered modern physics at the end of last year. Modern physics has a lot of little material. Okay. Then we also did a lot of all the optics you need. So you can go there and learn it. How we do it is we do little bit of optics right after we do electromagnetics, so that you understand light from the inside. Okay, and then we go to modern physics so that you understand the evolution of of physics. itself. So this is all beautiful material, and physics itself is beautiful subject. And that's why I wanted you to all know. Okay, so this is the rough breakdown of the portions. Okay, now for the JE students, right? See, you also have a lot of breakup, right? Now this is not like the other chart, but this is also a very good chart. Okay, now if you see the breakup will be very similar to this, slightly little bit this way, little bit that way, right? So about 10% optics, about 6 22 20% or so, you will get with modern physics, right? Then you have another electricity and magnetism. Then you have about almost another 20%, 25% of electricity and magnetism, right? A little bit less in the case of, surprisingly, for JE students. And then you have the laws of motion, etc. Mechanics is almost 35%. Okay, so 35%, 25%, 20%, 20%, and then 10%. Okay, so surprisingly, you have more weightage in the case of 1 minute. Just give me a minute. You have little more. Oh, okay. So I was going over the neat weightage. So neat weightage. See, roughly what we are doing is, one side we are doing this mechanics, right? The other side we are doing electrostatics and current magnetism, right? So class 12 students, we are doing electrostatics and current magnetism. Between the two, each is about one third. So one third mechanics, one third electricity magnetism. So we will first cover this material, then we do optics and modern physics and heat and thermodynamics. I just completed heat and thermodynamics. If you want to get ahead, you can just, listen to those lectures, and of course, you have to download the app. So now that is for the NEET students. JEE is roughly similar, but surprisingly, electrostatics and current, electricity, etc., is a little bit less. Electrostatics and electromagnetic waves, etc., is only 27, 26, 27%. Modern physics, on the other hand, is almost 25%, and optics is 10%. So because of that, and thermodynamics is 10%, then you have mechanics almost 30%, 30, 35%. Okay, similar, very similar. JEE is very similar to NEET. So today, getting to the material. So today we will do some problems also, so that you get comfortable with the problem solving in electrostatics. Okay, we already discussed conservation of charge. Charge cannot be created nor destroyed. Most charge, it is, you liberate electrons, you create a potential difference, and then electrons flow from one side to another, right? When you build a full circuit, electrons go around, and in the process, energy is liberated, right? So now the flow of electrons leads to energy in and so that is the idea behind pretty much electricity, right? So now at the subatomic level, you have electric charge, right? What is electric charge? You have electrons which have a quanta, right? Each electron carries 1.6 into 10 to the power minus 19 coulombs, right? And then there is conservation and quantization of charge. The least charge you can get is 1.6 into 10 to the power minus 19 coulombs. You cannot get charge even smaller than that. Okay, and so that's what it means to have quantization of charge. Inside an atom, the nucleus is 10 to the power of minus 15. It's so small. The atom itself 10 to the power of minus 10. There is another unit called angstrom. Angstrom is 10 to the power of minus 10. Okay. Now 10 angstrom makes 1 micrometer. Okay. So the atom is this big. The nucleus is that small. Okay, so someone was saying that if you take the head of a pin, right, as the nucleus, the roughly a stadium will be the size of the electron of the atom itself. Okay, so that's how tiny the nucleus is. Okay, so now charge is a very strong force. Okay, compared to gravity, which is considered to be a very weak force. Okay, so charge based force is much stronger. Then we looked at Coulomb's law, the inverse square law. Force is proportional to the product of the charges divided by the square of the distance between them, and we already looked at that, right? So now I'm going to give a simple problem. Previously, we looked at problems that came with the IIT PAL lectures. Okay, so today you see this problem. In this problem, you see three charges. Okay, there are three charges: Q plus Q, two charges of plus Q, and then one small q, and they are at a distance 0. They are placed at 0, d by 2, and d. Okay, so you have three charges here. One is 0, one is at d by 2, and the other is at d. Okay, now if the net force experienced by this charge, by the charge at q of q placed at x equals 0 is 0. Okay, if this charge experiences zero charge, okay, due to these two charges. Okay, if this charge experiences zero charge, then the value of q is what? Okay, so now this is a direct application of inverse square law. So now if you had two charges, you have principle of superposition, right? So you look at the force due to big Q, right? The force due to big Q and the force due to small q, right? So if you look at it from the field perspective, you can say that the field due to q, big Q, and the field due to small q at 0 is 0. Okay, so that is from the field perspective. So how do you solve this problem? Very simple. Compute the force due to, let's say you have, instead of plus q, you have a unit charge, right? At 0, right? Then what will be the force that the unit charge will face? It will be k q by d square. Okay, what will be the force the charge will face due to little q? K little q by d by 4 square, right? So d by 4, the 4 will go to the numerator, right? So when the 4 goes to the numerator, you will get 4 d, right? Because it is d by 2 in the denominator square, right? So now so it will become d square by 4, right? So d by 2, the whole square is d square by 4. So the d square by 4 is in the denominator, right? So now when the 4 goes to the numerator, you will have 4 qq by d square plus kq square by d square, right? So what is the force experienced by q at 0? It is 4 qq by d square plus uh, q square by d square times k. K you can drop, Now, when you drop the k, you will find that you end up with an equation which just tells you 4 little q plus 1 big Q, 4 little q plus 1 big Q equals 0. Okay, so you're merely applying principle of superposition due to the big Q at D and the little q at D by 2, and then you end up with 4q plus q equals 0. So q equals minus q by 4. If you see, they will always trick you with this plus q by 4, minus q by 2, plus q by 2, minus q by 4. So you must pick the correct answer. If you pick A, you will get wrong. I don't know if negative marking is there. JEE, I think negative marking is there, but NEET maybe it is not there. But whichever thing you're taking, you don't want to lose free marks, you know. So negative q by 4. Okay, d. You must pick d. When you solve 4q plus q equals 0, and that must be very obvious, right? If one charge is repelling, the other charge must be attracting, right? The big Q and the big Q will be repelling, like forces repel, right? So the little q has to attract it to make it 0, to make the net force 0. So it has to be negative, right? So you must, also look at these things. Blind solving never works. So and you, it's not difficult. These things you just have to look and carefully do. Okay. So now this is second problem. Second problem involves little bit what you learned in the other mechanics also. Okay. Sometimes they will include little bit mixture of two things. Okay. The bob of a simple pendulum has mass 2g, 2 grams, and a charge of 5 microcoulombs. It is at rest in a uniform electric field of intensity 2000 volts per meter. Okay. Now, volt per meter is also Newton per coulomb. Okay. Electric field intensity means it's only, one thing. Okay. Newton per coulomb is same as volt per meter. Okay. We will come to that little bit later. Little bit we saw last time also, but dV by dx is E, right? So volt per meter. At equilibrium, the angle that the pendulum makes with the vertical is, okay. So let's understand what's going on here. See, firstly, little bit you have to spend extra time in physics, when you solve the problems, okay? Because first you have to read the question, then you have to correctly answer it, okay? So two things are happening. One, there is a free body diagram you have to draw. There is a simple pendulum which has normal, one tension, one mg, one, and then it also has another force which is based on electrostatics. Okay, if you just hung a simple pendulum, it will just hang straight, right? But now, what is happening is there is also a electric field. Okay, it is at rest in an electric field. So the electric field, in the electric field, the pendulum swings. Okay, but it swings so much, only so much, because the tension is there. Okay, so now how much does it swing? The more it swings, the greater the tension, right? So now if you see the free body diagram, right, the electric field is horizontal, right? So the tension has to neutralize, because it's at rest. At equilibrium means it's at rest. So the net force on the pendulum bob is 0. What are all the three forces? Free body diagram. Okay. Free body diagram, what is there? Mg, downwards. T, right? Tension, right? So those are the two forces. And then there is electric force. Okay. Electrostatic force. Okay. So it is a charge pendulum, right? So now, what is the force due to electrostatics? It's field times Q, EQ, F equals EQ, right? Electric field is the force per unit charge, right? Newtons per coulomb. Force per unit charge is electric field. So E times Q will give you the force, right? So EQ horizontal equals, now if theta is the angle, right? T sine theta, right? T cos theta equals mg, right? T cos theta equals mg. See, tension is going to neutralize both the electric force and the both the electric force and the weight. Okay, so T cos theta equals mg. T sine theta equals eq. Okay, so two equations and two unknowns. Now you divide the two, right? You divide the two, you end up with EQ by mg equals tan theta. You want to eliminate the t, right? So there are only two ways to eliminate the t. One is you square and add, right? If you square and add, you won't eliminate the t, you will eliminate the theta, right? So then you solve for the t and then you can plug it back in, That's not the right way. That is one way to do it. The other way is just divide the two equations. T will disappear. T will cancel, right? T sine theta equals something. T cos theta equals something. So if you divide equation 1 by equation 2, you will get on the left side EQ by mg. On the right side, you will get sine theta by cos theta. T will cancel. Sine theta by cos theta is tan theta. Tan theta equals EQ by mg. So theta equals tan inverse of EQ by mg. So then you plug all that thing and calculate the EQ by mg, and you will get some number. In this case, all that when you simplify that number, you get 0.5. So tan inverse of 0.5. Okay. Now it took a little bit of time. Okay, but it is not difficult. Okay, so that's what I want to emphasize. Okay, so if you understand the material, you understand free body diagram, you understand F equals EQ, Mars is there. Okay, so see, don't think I'm only emphasizing marks. I want all of you to do well. You know, some of you should do really well. That's why we make sure that you also are keeping full effort to do well and succeed. Now, electric field, okay, like gravitational field, every charged body produces an electric field, right? And the field at every point around it, okay. So gravity we already know, right? Any body has a gravitational field, and it attracts every other body in the universe, right? The earth attracts everything. Drop it, falls. Drop it, falls. Right? Attracts everything. Similarly, a charge also attracts everything around it. So everything that is charged around it. If it is a neutral charge, it won't attract. It doesn't care. Okay. But electric field, if you have another charge, it will attract it. Okay. So that is this idea of an electric field. At every point around in the space around, there is a field. Okay. And if there is some charge kept at any point in the field, it will be attracted by this, according to Coulomb's law. Okay. And what is the value of the field? So at every point, there is a vector field. Field is the force per unit charge. Okay, and it exists at every point around a charge. Okay, all right. And there you have this idea of superposition of fields, which is what this problem was about. Okay, so here is a superposition of fields, right? Superposition of fields, and so when you compute it, you just add the vectors, right? And therefore you must do vector addition when you do superposition of electric fields, because it's a vector. Okay, now inside a conductor, okay, this is an important idea. Okay, let's say there is a conductor. Okay, inside the conductor, due to the conductor, okay, let's say there is a hollow conductor. Okay, inside the conductor, assume there is no charge. Just there is some liquid or there is vacuum. There is no charge. Okay, there will be no electric field inside a conductor. Okay, this is a very important idea. Okay, in a conductor, the charge will always float out to the surface of the conductor also. Okay, if you have a solid conductor, right? If you had a solid conductor like a mass ball of iron, right? So metallic ball, if you had and you charged it, all the charge, like the bob here, this pendulum bob, right? Let's say it was made out of metal, right? All the charge will go to the surface of the conductor. Okay, and inside there will be no electric field. Very surprising idea. Very surprising idea. When they first told me, I didn't believe it. Okay, but you must remember this, because they always test students about this idea. Okay, so and the value of the electric field is 1 by 4 pi epsilon naught q by r square. At any point, it is the force that is experienced by a unit charge at that particular point, kept placed at the particular point. Okay, so if they gave you E, then you can do EQ. Okay, so in this case, he is first computing the E due to a point charge, and then he's computing the EQ. All right. So next, next is this idea of work. Okay, so superposition of fields. If there are two fields, then you have, you end up with, corresponding charge. Okay. Now, what is the electrostatic potential due to two charges? The potential is 1 by 4 pi epsilon naught Q1 Q2 by R. Okay, so if you have two charges, the electrostatic potential of one on the other is 1 by 4 pi epsilon naught Q1 Q2 by R. Okay, so dV by dx is E. Okay, so if they gave you E, right, it is you do E dx, integral of E dx, you will end up with V. If they gave you V, you just differentiate with respect to R, you will end up with E. dV by dr, the gradient of the potential, dV by dr will give you. Okay, now potential is very related to this idea of work. Okay, and so that's the next thing we are going to study. Okay, so there is three or two or three types of fields, right? Now the electric field is the best, is electric and magnetic fields are have to be very well studied in electromagnetic theory. Okay, now right now we are doing electrostatics, right? Now, but there are other types of fields. There is a pressure field. Okay, pressure field is, if you had if you study well, when you study fluid dynamics, or when you study high pressure environments, right? PV equals nRT kind of environment, there will be a pressure field. Like if you look at a plant, right? You have to be very careful. Everything is under high pressure. Like you look at a what is that? Steam engine, right? Steam engine, there is so much pressure buildup. So you must be very, very careful in terms of the pressure buildup. Now there can also be a temperature field. If there is a very hot body, there will be a temperature field. And you have to study that also, because many things with temperature, they crumble, and or long-term exposure to temperature causes it to crumble. Most important place where you will see that is in an IC engine, that is in a car, right, or a scooter. So inside the scooter they are burning the petroleum, right? You pour gasoline in the tank, then or motorcycle or car, right? The IC engine, they burn the petroleum, and then that pushes the pump. That creates a pump effect. So four-cylinder engine, the four cylinders will move in synchrony, and that is converted. That synchrony with which it moves causes the wheels to rotate, right? And so the inside the engine there will be a high temperature gradient. Okay, and then they have this water that comes and cools the engine. There are some, of course, you can also have air cooled engine, right? Not everything has water cooled, right? So air cooled engine. So there is a pressure gradient. You have to study all these things when you do physics. So now the dipole, right? We all then looked at the dipole, right? And then we introduced this term called dipole moment. So what is a dipole? Two charges, equal and opposite charges, separated by a distance, right? And that distance we normally call it 2a, right? And so we then introduce this term called dipole moment, which is what is that? Q times 2a, right? Q times 2a, right? What is dipole moment, right? Q times 2a times I, right? It goes from positive to negative to positive, right? So the dipole moment is Q times 2A times I, right? So you have negative charge, then you have positive charge separated by distance 2A. So it goes from negative to positive, right? And so that is the direction of the dipole moment. And now, if you had a positive and a negative, right? Now, of course, you are separating them so that they don't come together, right? So now a dipole moment. See, anytime they use the word moment, it means that it is going to cause a torque. It's going to cause some kind of rotation if you let it go. Okay. So that's why if you put a dipole in an electric field, let's say there is an electric field, right? One side is going to be attracted, the other side is going to be repelled, right? It is going to push this one and pull that one. So it's going to kind of have a rotational impact on it, right? And therefore the torque experienced by a dipole is P cross E, where P is the dipole moment, right? Q times 2A, right? So it goes from positive to negative. So when it's in the field, it will experience a torque which is given by P cross E. So there is a constant field, okay? So now, because if it starts rotating, then the cross product will be based on the sign, right? When we say sign, I mean sine theta, right? P cross E is PE sine theta, right? Therefore, that will change. See, the P itself is not going to change. Q, the charge is not going to change. The distance separated typically is not going to change, right? In a dipole moment, right? It could, but typically, they don't allow that. So if you have a uniform field, let's say it's a horizontal field like that, right? Then you have a dipole, right? So P cross E will cause a torque. Okay, so we will come to that. Okay, so now, this is we are looking at the impact of looking at the electric field due to the dipole. Okay, see, when we do P cross E, we are saying there is an external field. Okay, now here the dipole itself is producing a field. Okay, so you have one charge, you have another charge. Now, if you take a point here, right? If you take a point at the center, right? What is the electric field at the point at the center? It will be zero, right? There will be one charge. If you put a positive charge here, it will not be zero actually, right? If both were plus Q, it will be zero, right? But here it is not going to be zero. Okay, why? Because the negative charge is going to attract it. The positive charge is going to repel it. So it is going to be twice the net effect, right? So at that point, it is going to have twice the effect, and therefore that point will probably have the maximum field. Okay. Now, if you take a point like this point, okay, at this point, right? At this point, this is going to attract. If you take this point, this is going to, if you had a plus Q here, this is going to attract, right? And this one is going to repel. So you have one force like that, another force like this. So you have the field here due to this one is going to be that way. The field due to this one is going to be this way, right? Now, because this is symmetric, you can say that the vertical components are going to cancel. So it is only going to have a horizontal component. Okay. So along the diagonal, it will only have horizontal components. Okay. What is the value of that horizontal component? It is going to be the sum of these two. So if you see, when he adds up, he will cancel out the j, right? So if you say this is I and this is j, the j components will cancel out, right? Sine theta, right? Minus cos theta I plus sine theta j minus cos theta I minus sine theta j, right? So now the I components are additive, so that in this direction, so the net force is in this direction because this is positive I, so the net force is in this direction, right? The j components are going to cancel each other out. So the net j component at that point is at all the points in the perpendicular bisector is going to be 0, and so the only component is going to be in this direction, is going to be that way. Okay, so E q of plus q plus E of minus q is q by 4 pi epsilon naught r square times negative 2 cos theta I. Okay, and so now what is cos theta? Cos theta is A by R. Okay, and so you plug that in. So negative 2A times QI is P, right? So negative P by R cubed. Now, if it is very far away, R and Y will be the same. That's what he's saying, right? So it will become negative P by 4 pi epsilon naught Y cubed. Okay, so at a long distance away from a dipole, it is P by 4 pi epsilon naught Y cubed. Okay, so more the P, the higher it is, and it is almost the cube of the distance, because P is a constant. The charge is a constant, the distance separating the two is a constant. So a very large distance away, the electric field due to it will be a negative P by 4 pi epsilon naught Y cubed. Okay, so if they ask you a question like this, you should know. Okay, you can treat a atom with a hydrogen atom with one electron, one proton, or even any other atom like a dipole. And so if you're looking at a very far distance, it is P by 4 pi epsilon naught Y cubed. Now, a dipole, as I said before, a dipole in an electric field will experience a torque, right? It will tend to, so in this electric field, one side is going to be repelled and the other side is going to be attracted. So anytime you have repulsion, attraction, it will cause rotation, and the net torque is P cross E. So the net torque is P cross E is what a dipole which is kept in an external electric field will experience. The dipole will tend to spin. Okay, so if they gave you treat something like a dipole and it is kept in a uniform electric field, then it will cause it to spin, right? Now, in a non-uniform electric field, what does non-uniform mean? That the field is not the same at every point. Okay, the non-uniform electric field, there is a net force. Okay, what is the net force? See, in the uniform electric field, the two will experience the same E, right? Therefore, you have this E and that E will cancel out. The force on this and the force on this will cancel out, but there will be a torque. Okay. Now, in a non-uniform field, there is a net force because the E on the positive side, the E on the negative side are different. That's what the meaning of non-uniform is. Uniform means the value is a constant. Non-uniform means the electric field is changing with position. So the E at negative Q is different from the E at positive Q, right? That's what he's saying. You see the last line is saying E of negative Q is greater than E of positive Q. Okay, so that's what's going on there. Okay, so let's look at the torque problem. An electric field of 1000 volts per meter. I told you dV by dx is electric field, right? Is applied to an electric dipole, right? So P cross E at an angle of 45 degrees. He wants you to do P cross E, right? The value of the electric dipole is 10 to the power of minus 29, right? So P coulomb meter, right? P is 2, what is that? Q times 2A, right? So that's why it is coulomb meter, right? So P cross E will be 10 to the power of minus 29 times 1000 times sine 45 or cos 45, right? So you should so P cross E is the dipole moment. It should give you sine 45, right? The potential energy or work is P dot E. Okay, so the potential energy or work is P dot E. The torque is P cross E. Potential energy or work is P E cos theta. So that is also 10 to the power minus 29 times 1000 times cos 45. Okay, 7 into 10 to the power minus 27 joules. Okay, P dot E will give you work, P cross E will give you torque. An electric dipole is placed at an angle to a non-uniform electric field. See, all these questions, they are trying to trick you a little bit. Okay, that's why you learn all the material, you must learn every idea. Okay, now a dipole is placed at a 30-degree angle to a non-uniform field. The dipole will experience what? Will there be a force? Net force. Yes. Right? Will there be a torque? Yes. It will have both. Two forces at different points will cause a torque, but there is also a net force because the field is non-uniform. If the field is uniform, only dipole will experience zero force. Okay, so that is the point here. Okay, this problem is essentially testing you the concept. Lot of questions in NEET will only test the concept, but the JEE questions will test both. NEET don't think that they will not test some simple mathematics. Also, simple mathematics can be asked, very simple ones. Okay, not too much lot of calculations, etc. They often avoid, but sometimes they can ask. You should be ready for everything. Okay, so now electrostatic potential. The electrostatic potential is also a scalar. It is similar to gravitational potential energy. It is very related to work. Okay, so E F dot dx is work, right? E dot dx is electrostatic potential. Okay, it is a scalar. Okay, now it is linked to the idea of doing work or when work is done. Okay, now taking the gradient of the electrostatic gradient is like this. Okay, the gradient, see, typically if you have a scalar field, right, that scalar field will vary in a certain way, right? The gradient is a vector. The gradient of something is a vector with respect to distance. So at any point, you get the variance and you also have a direction associated with it, the net variance. Okay, so the gradient will produce a vector from a scalar. Okay, a scalar field will be a function of x and y. Okay, now when you take the vector derivative of it, you will get a vector. Okay, so remember that, and we will come to that again. Okay, now electrostatic potential. Electrostatic potential. See, like when you have when there is work done by an external force. So there is an external field, right? So the external field is going to do work, right? Now, what work will it do in bringing a unit positive charge from infinity to the point, right? So when we look at gravitational potential energy, it is very similar to this idea. Gravitational potential energy is sometimes it is just defined relative to one point and the other, right? See, if I tell you that I'm lifting something from this point to this point, I am I'm doing certain amount of work. Mg is the weight. I'm moving it up h distance of h. I'm doing work equal to mgh, right? Now, similarly, when you move a charge in an electric field from one point to another, you are doing work. Okay. Now, how much work you have done is said to be, or how much work it is doing, right, is said to be dependent only on the two end points. It doesn't matter where all you go. Only the initial and the final points matter. So now, what is the potential? Let's say there is a point charge. What is the potential at this point? What is the electrostatic potential at this point? The electrostatic potential at this point is the work done to move something from move a unit charge from infinity to that point. Okay, so that is defined to be the electrostatic potential. Now, if you had point 1 and point 2, right, you can define what is called a potential difference between these 2 points. Okay, now electrostatic potential is dependent on position, right? Now, as you go further and further away, it decreases, right? Now, at least in magnitude, right? Um, so now, um, like because it's like inverse square law, right? Inverse square law, the larger the R, the lower the potential, right? So now, if you had 2 points, right, you just subtract the potential of these 2 points, you have what is called as the electrostatic potential difference. Okay. Now, if you have an electrostatic potential difference, right, it takes work to move something from one point to another. Okay. So the energy taken to move from one point to another is the electrostatic potential energy. Okay. Now, in these electrostatics, right, you have again E dot dl, EQ dot dl, right? EQ is the force, F dot dl is the work, right? Therefore, EQ dot dl is the work, right? If you had two charges, right, or if you had Q3 in two electric fields, the net work will give you the net work done will be computed by the superposition principle, right? Work done from due to one field, work done due to the other field. Okay, so Q1 Q2 by R, Q2 Q3 by R, Q1 Q3 by R, Q2 Q3 by R, right? And so the two R's will be different because the two charges are in two different places. Okay, so the work done to counteract both the charges will give you the total potential energy. So it is a summation, right? So you have the electrostatic potential due to two charges at this point, electrostatic potential due to these two charges at the other point. So what does it take to go from here to there? It is the difference in the net electrostatic potential at each of these points. So subtract the two, you will get the potential difference. That is the work it takes to move from one point to another. Okay. Quickly, I am going through so that because that is how it is. Okay. So work done by the external force to take a unit charge from Ri to Rf is the electrostatic potential difference. Okay. So it's this is a scalar, that is a vector. Now, remember that it is a dot product. So if E is in this direction and you are moving in this direction, right? What can you say? If E is in this direction, you are moving in this direction, there is no work done, right? The dot of two vectors which are perpendicular to each other is 0, right? So now, if it is along the same direction, if E and H is in the same direction, then you have, when you take the dot product, the AB cos theta cos 0 is 1, right? So it will just be the product form, right? So in this case, he has E in this direction and he is moving it in along the from xi to xf. So the initial position is xi, final position is xf. The E is in this direction, so EQ times xf minus xi. Xf minus xi is h, so QE times h. Okay, so the dot product is a dot B is AB cos theta, A and B, the two are the same direction. The L and F dot L is in the same direction. So the work is a dot product, right? So, so that is the idea there. W equals Q E naught Q H. Okay. So let us see how we are doing on time. So we have only few more minutes. Let me go a little bit further before we kind of wind it down for today. So path independence. Okay. So what path independence says is that it doesn't matter in which direction you go, right? So if you are in an electric field, right, or in a place with electrostatic potential difference, right? It does not matter whether you go from A to C to B, A to B, D to B, or A to B directly. Okay, which road you take does not matter. Very surprising idea, right? Normally, if you have to go from Madras to say Coimbatore, right, you could go through many different ways, right? But that does not matter in electrostatics. Okay, whichever path you take does not change the net force. Okay, does not change the net potential or the net work done. The force will change at each of the points. The force will be different, right? But the net work done is a sum total, right? So that sum total, it is an integral, right? Integral f dot dx is a sum total, right? So that sum total, the net work done, does not depend on which road you took, which path you took. Only depends on the initial and the final endpoints. So if you had a uniform field, you just do ZF minus ZI, XF minus XI times EQ. Okay, so that is the path independence of work. Okay, so the total work done EQ times XF minus. All right, all right. So now the path independence of forces of is true of all what are called conservative forces. Now conservative forces are of the form where the force is just a function of the distance. Okay, if you can write the force as f of r, where r is distance, then you can say that it is a conservative force. Now, electrostatics is, as you know, k q1 q2 by r square. So that r square in the denominator, that is the only changing element. So because of that, we say that electrostatics is a conservative force. Therefore, there is associated with it path independence. Okay, so that is a very important other idea. So here he has a point charge and he is doing work in that point charge. I will be taking this problem next class. Okay, but understand that another point in path independence. The other point in path independence is that if you go one full circle and come back to where you started, right, you would have done zero work. Integral f dot dl will be equal to 0. Net work done in any closed path is equal to 0. Okay, so remember that also. So these are all specific ideas in electrostatics. So I was hoping to do one or two more problems and then get to Gauss law. Unfortunately, has to wait another day. So next time I will start with Gauss law, but then we will come and do one or two problems with electrostatics also. So with that, I am going to end today's lecture, and I'll see you all again next class. All right. So if it's Sunday, it is for now it is electrostatics. Then we will go on to additional material. As the semester or the year wears on for the class 12 students. All right. Okay. Thank you.